Good. It's also over on the side. All right, so we're in section 2.2 today. We're talking about higher degree polynomials. So yesterday we talked, everything was about quadratic polynomials. So our highest power on x was 2. Today we're going to talk about higher degree polynomials. First thing that we want to do is, everything that we're talking about today has to do with how polynomials behave, what their graphs look like, just in general, how do they behave. So a couple of important things about polynomials is that one, that they are continuous. And that's going to be an important property for functions as you go forward in calculus. Continuity is a big thing. Continuous means that there are no gaps in our graph. No gaps or jumps. So if we had just a quick sketch, if we had a piecewise function, something like this, we've dealt with functions like this before. If we had a function like this, that is not a polynomial. So our graph doesn't ever have a gap, doesn't ever jump. So this would not be a polynomial. And the other important thing about polynomials is our graphs are smooth. So it means no sharp turns. So something like an absolute value graph would not be a polynomial. So if we had something like this, where we have this sharp turn here, the sharp corner, this is not a polynomial. So our polynomials are continuous and smooth. This idea of being smooth, that's another important idea that we'll give it a more technical name when you're in calculus. But polynomials are nice. They behave nicely. That's one reason that we like them. All right. So yesterday when we talked about quadratic polynomials, we said their graphs were parabolas. So y equals x squared. We know it opens, graph is a parabola, and it opens up. So just a quick sketch of y equals x squared. And it keeps going on the right hand and the left hand side, it keeps going up. It doesn't ever turn around again. And y equals negative x squared. Same thing, but it opens down. So our graph is going to keep going down like so. And it doesn't turn around again. And it turns out that any polynomial where the highest power is even, eventually on the right and left hand side, either goes up on both sides or down on both sides. So y equals x to the 4th looks more or less like this. Y equals x to the 6th looks more or less like this. And if we have some other complicated polynomial, but the highest power is even, eventually on the left and right hand side it goes up or down. And let's look at a odd degree polynomial. Oh yeah. So y equals x to the 3rd. Do we remember what the graph of y equals x to the 3rd looks like? But kind of an S shape, right? So it looks kind of like that. And on the right hand and the left hand side, here it keeps going up and here it keeps going down. It doesn't turn around again. And y equals negative x cubed. Same thing, but we flip it over, reflect over the x-axis. So it would look something like that. And it would keep going up and keep going down that way. It doesn't go straight. And it turns out that any odd degree polynomial eventually on the right hand and left hand side does the same thing. Goes up on one side and down on the other. So x to the fifth, y equals x to the fifth, looks more or less like this, x to the seventh, etc., etc. Same for the negatives. Turn it over, reflect it over the x-axis. That gives us a way to figure something out about the graph of our polynomial just by looking at the term with the highest power. So that gives us a test, a way to know what happens eventually to our function. We call that the leading coefficient test. Is everybody good with this? So our leading coefficient test. The leading coefficient test tells us on the left-hand side and on the right-hand side, as x gets very large, x gets very small, what does the function eventually do? Does it eventually do this, 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 or this? So when we're talking about our leading coefficient, for our polynomial we said was a to the n, x to the n plus dot dot dot, and our exponents got smaller and smaller and smaller. So we're looking at this term. This is the term that we're interested in. So we're going to make a little chart here for our leading coefficient. So in this column we're going to put a sub n x to the n. Here we're going to say for this column we're going to say a sub n is positive. So our leading coefficient, this number is positive. And for this column I'm going to say a sub n is negative. And here for this I'm going to say n is even. Here I'm going to say n is odd. So if n is even and our leading coefficient is positive, it behaves like y equals x squared. And all we have to do to tell what it eventually does is draw a couple of arrows. Eventually it does this. It could do all kinds of crazy stuff in between, but eventually it's going to go up on both sides. And if a sub n is negative, eventually it goes down on both sides. Could do all kinds of crazy stuff in between, but eventually it goes down on both sides. If n is odd, our highest power on x is odd, and this number is positive, eventually it behaves like y equals x to the third. It does that. And if the highest power is odd and this number is negative, it does the opposite. Eventually it does this. And the way the question would be asked is the right hand and left hand behavior, the n behavior, what happens as x gets very large, what happens as x gets very small, as x gets very large, x gets very small. So all of those different ways could be ways that you might be asked this question. So what happens to our function eventually? Polynomials all eventually do one of these four things.
So we ever have to graph that?
So the answer to the question is just drawing these little arrows.
Oh, okay.
So let's look at an example. So an example would be describe the right and left hand behavior. The other way you might see it asked is the end behavior. So what's happening at the ends of the graphs and we'll do a couple here. F of x equals minus x to the fourth plus 7x to the third minus 14x minus 9. So all we care about for this kind of question is the highest power on x, the term with the highest power on x. So that's all we're looking at. The highest power is even. The leading coefficient, negative. We have a negative sign there. So eventually, what does this thing do? Does this. And our answer to our question, there's a description of the right and left-hand behavior. That's the answer to the question.
What if there's a number, like a sub n is a number that changes anything?
Nope. All that matters is whether it's positive or negative. Doesn't matter what the number is. All we're interested in is it positive or negative. Is this even or odd? You could say it goes down on both sides, it gets smaller on both sides, but to answer the question, all you have to do is draw those arrows. And if the terms are scrambled, if this was written in a different order, we always look at the highest power on x. It's not always the first term, it's the highest power on x. So if we had, for example, 5x to the fifth plus 2x to the third minus 14x squared plus 6. All we care about for this is that term. And what would be the eventual behavior, the right and left-hand behavior of this one? Down on the left, up on the right. And that's the answer to the question. It could do all kinds of crazy stuff in between. It could move all around. We don't really care what it does. But eventually, it's going to go down on this side and up on that side. Right now, we're not interested. For this question, we're not interested in what happens in between. We'll talk about that in just a second. The right and left-hand behavior just means what happens eventually. All right, we good there? Yes.
This is kind of complicated, but would a graph, the polynomial graph, would it ever like intersect itself?
Nope, never intersect itself. It's a good question though. And so when I drew those scribbles in there, I wasn't drawing polynomials, right? No, they always, they're nice and smooth and yeah. The vertical line test would tell us whether or not it's a function. And we know polynomials are all polynomials pass the vertical line test. So, all right. One big thing that we're going to be interested in this chapter, kind of one of the main ideas, is finding the zeros of a polynomial function, finding the x-intercepts. So we're going to talk, I'm going to make a list next of some terms that all mean the same thing. Because the questions will come up in different contexts, and we'll need to know that all of these things are referring to the same idea about a polynomial. And they have to do with, all of these ideas have to do with the zeros of a polynomial. And a part of what we're doing is, if we know what happens at the ends of our polynomial, we know where they cross the x-axis, then we can figure out, we get a good idea of what the graph looks like. So we're kind of zeroing in on what our graphs of our polynomials are going to look like. So for all of these conditions, we're saying f of x is a polynomial. And a is a real number. So we're going to list 4 conditions that all these four things mean exactly the same thing. So x equals a is a 0 of f of x. That is the same thing as saying x equals a is a solution to f of x equals 0. So we talked about this yesterday. To find the 0 of a function, we set the function equal to 0 and solve. So saying a is a 0 is the same as saying a is a solution to this equation. So these two things mean the same thing. This is also the same thing as saying x minus a is a factor of our polynomial. So what do we mean by a factor? So isn't factoring one way we find zeros, find solutions? Then we do that on some of these examples, we factor. So that means x minus a is going to be one of the parentheses that we get when we factor that polynomial. So we can factor that polynomial into these multiple parentheses that we're multiplying each other. If x equals a is a 0, or x equals a is a solution, that means x minus a is a factor of that polynomial. That's something we can factor out of that polynomial. And the last one that's equivalent is that the point a0 is an x-intercept of the graph of f of x. That's something else we talked about yesterday. To find an x-intercept, we set the equation equal to 0, and we solve. Whatever our answer is gives us the x-coordinate of our x-intercept. So all 4 of these things mean the same thing. And they will come up in questions in all 4 of these different ways. And it's going to be important that we understand that all of these things mean the same thing. So we can translate back and forth between those 4 things. Because we'll have to find our answers in all of these different ways. We'll have to factor, we'll have to find a solution, we'll have to find x-intercepts, we'll have to find zeros. That's a big topic of what we're going to do in this chapter, or what we are doing in this chapter, is finding zeros. All right, 2 other important properties of polynomials. We're going to say f of x has degree n. So our highest exponent is n. If our polynomial has a highest degree n, f of x has at most n real zeros. So a 3rd degree polynomial has at most 3 real zeros. It could have less. So if we have a 3rd degree polynomial, we could potentially factor that polynomial into 3 sets of parentheses. Sometimes we get less than 3. Sometimes our 2 of our roots, we could have complex roots, could have imaginary roots. Has at most n real zeros, and f of x has at most n minus 1 maximums or minimums. So our quadratic polynomial, n equals 2, has 1 maximum or minimum. A cubic polynomial, n equals 3, would have at most 2 bumps in it, basically. So So it's another way to look at, to get information about our polynomial. How many times can it cross the x-axis? How many times can it make a curve? Basically. Turn around from going up to going back down. All right, so let's find the zeros of a polynomial and see what that tells us about our graph. So let's find the x-intercepts of f of x equals x cubed minus x squared minus x plus 1. All right, so it's asking us to find the x-intercept. So we need to relate two of those things that we said are the same. How do we find the x-intercepts of a polynomial? Solve it, and we solve it by doing what? Setting it equal to, what did you say, Matthew? Set it equal to 0. Yes, we're finding the zeros. We're solving. So we say x cubed minus x squared minus x plus 1 equals 0. We set y equal to 0. We're solving this equation. All right, how do we solve this equation? Well, we can't take the cube root because we end up with having to take the cube root of everything, yes?
Subtract 1 both sides and
So you're on the right track with a common x. If we just had an x squared and an x and a 1, how would we solve that? What would be our first choice? Factor. Let's factor. So there's our second, another equivalent statement. We want to factor this. We have 4 terms. What is that? What kind of factoring does that suggest? Factor by grouping. So I'm going to factor these 2, and I'm going to group those 2 and those 2. What can I factor out of this group? X squared. So I'm going to write that as x squared times x minus 1. And what can I factor out of this group? Let's factor, we want negative 1. So let's factor a negative 1. And we get x minus 1 equals 0. We have a common term of x minus 1, so this is, let's factor that out, x minus 1 times x squared minus 1. Can we factor this more? X squared minus 1? How does that factor? X minus 1 times x plus 1. And then I'm going to rewrite these. I'm going to write this as x minus 1. And then I have the parentheses squared times x plus 1. All right, so what makes this now? What makes this equal to 0? X equals negative 1, and x equals positive 1. And our x-intercepts are points. So our x-intercepts are going to be negative 1, and what's y equal at our x-intercept? 0 and 1, 0. So those are our x-intercepts. If I sketched a graph of this thing, our graph would look something like this. So the leading coefficient test tells us it goes down on the left and up on the right. It crosses the x-axis at negative 1. It touches the x-axis here. And it has 2 maximums or minimums. It has 1 maximum, 1 minimum. And we have only 2 zeros. And notice that here where x equals 1, the power on that parentheses is 2. And where x equals negative 1, the power on that parentheses is 1. And for one, we cross the x-axis. The other, we touch the x-axis. Well, there's a rule about the powers on these parentheses that tell us whether our polynomial crosses the x-axis or touches the x-axis at our x-intercept. That's the only two possibilities at an x-intercept. So it can cross or it can touch. And we'll talk about that next. Everybody good here? All right. Last thing we need to talk about is multiplicities of roots. All right, so multiplicity of roots. What we're talking about here is we have x minus a to the k power is a factor of f of x, which is a polynomial. If k is greater than 1, so we have our parentheses raised to a power. If k is greater than 1, then we say that a is a repeated 0. And we say it has multiplicity k. If k is even, the graph touches the x-axis at x equals a. And if k is odd, the graph crosses the x-axis. At x equals a. So when we factor our polynomial, when we solve our polynomial, when we get our zeros, we have a parentheses raised to an exponent. That exponent is odd. The graph crosses the x-axis at that intercept. If the exponent is even, the graph touches the x-axis at that intercept. We can think of it as being like y equals x squared and y equals x cubed. X cubed, we cross the x-axis. X squared, we touch the x-axis. Same kind of idea. Yes? So let's go back here really quick. I think so. The x equals 1, the number that makes this equal to 0, would have multiplicity 2. This one where x equals negative 1, that makes that 0, that would have multiplicity 1 because this exponent is just 1. So since this is multiplicity 2, our graph just touches the x-axis there, since that's even. And here x is 1. Our graph crosses the x-axis. Okay? All right, we good there? So another tool to help us analyze a graph of a polynomial. All right, the last thing I just want to give you some steps for graphing. Some of your homework problems will ask you to sketch a graph of a polynomial. So we have lots of tools that we can use for graphing. One, we're going to use the leading coefficient test. So we figure out what our graph's going to eventually do on the right and left hand side. Two, we want to find the x-intercepts. So we want to find where a graph crosses the x-axis. We do that by setting y equal to 0 and solving. 3, we want to use our multiplicity of our roots to decide does the graph cross or touch. And then between our zeros, to decide whether the graph goes way up before it comes back down and crosses the x-axis again, we need to plot an additional point or two. So plug some numbers into your function and calculate. And then we also know that our graph is smooth and doesn't jump, so we sketch our graph, sketch a smooth graph. So we connect our points that we found with a smooth graph. So some of your homework problems will ask you to sketch a graph, and on a quiz or a test I'd ask you to do that without using your calculator. So you'd have to use all of these ideas to sketch your graph.